Hi, everyone. Thank you for joining us for the next installment of the CPU 2AL speaker series. Today, we will have a presentation from Dr. Edward Thomas from Auburn University. He serves as the Associate Dean of Research and Graduate Studies in the College of Science and Mathematics. And today, he will be talking about dusty plasma, not just the fourth state of matter, but all states of matter. So without further ado, take it away, Ed.
Great, thank you, Dana, and welcome to everyone. And I hope that maybe you'll learn something fun and interesting about this interesting problem that we have been looking at for many years, which are called dusty plasmas. As Dana said, my name is Edward Thomas, and before getting started, I want to acknowledge all of the various supporters of this work, particularly the National Science Foundation, which funded a lot of the facilities. Of course, the NSF EPSCoR project, which funds the CPU 2AL project, Department of Energy, which supports our facility, and some of the work that I'll be talking about at the end here will be based on some microgravity work that we're doing, which is supported by NASA. And so just as a brief outline, the talk will sort of focus on three main topics. First of all, why I think dusty plasmas are interesting and why it's a really wonderful system to study. I'll talk a little bit about the fundamental physics of the so-called dusty or complex plasmas, and then really getting into the meat of the talk at the end of how do we use dusty plasmas to study other states of matter. And in particular, I'm going to highlight two examples. One is using dusty plasmas to look at liquid-like properties, and the other one is to use dusty plasmas to look at solid-like properties. So let me begin with this question of why dusty plasmas are interesting. And they are certainly really interesting to me. And so let's go with that. So first of all, what do we mean by a plasma? A plasma is a type of ionized gas. You can find plasmas in both natural environments and a variety of human-made environments. In the upper part of this image here, you're seeing a number of human-made applications of plasmas, everything from fluorescent lighting, which inside the fluorescent light bulbs, there's a plasma, to manufacturing, plasma medicine, agriculture, using plasmas for both of those kinds of applications, fundamental laboratory experiments, and then looking into the future using very hot plasmas to produce energy in the form of fusion energy. And then, of course, there's many kinds of naturally occurring plasmas, from lightning, all the phenomena associated with what's called space weather, the local plasma environment around the Earth, astrophysical objects, and then star and planet forming regions, which will have a mixture of plasma and other materials mixed together. Now, one of the things that ties all of these kinds of plasmas together is that you can have embedded solid particles inside of these plasmas, and that's what we refer to as the dust. And that is the basis of why we think that these systems are particularly interesting, because you can get these dust-laden plasma systems or dusty plasmas. Now, it turns out that people have actually, and researchers have been studying this idea of having solid particles or solid particulates in plasmas for a very, very long time. And one of my colleagues actually found a very old paper from 1924 by one of the fathers of plasma physics, Irving Langmuir. And at the beginning of this paper, he talked about under certain conditions, the globules, these little objects, move around very slowly so that their motions can easily be followed by the unaided eye. And as I get to show you images of the kinds of dusty plasmas that we form in the laboratory, that description of globules moving around a plasma from 1924 sounds very much like the kinds of dusty plasmas that we see in the laboratory today. So I think of it as an old topic that we've begun to study again. So dusty plasmas have been as I mentioned, have been used in astrophysical and planetary systems for some time. Kind of the modern study of of dust in plasmas was really kind of motivated by studies of Saturn's rings. And so in this lower image here on the left, there's this image of Saturn's rings taken by the Voyager spacecraft back in the 1980s. And then there's these black structures that you see here. The rings go around the planet, and then there's these spokes. And these spoke-like structures are believed to be charged dust that's sort of floating around the rings. Some 30 years later, almost 40 years later, when Cassini went to to Saturn, another space mission to Saturn, here are the rings again, and then you see again these broad structures here that are hovering above the planetary rings, which was, first of all, really good confirmation that what we saw in Voyager was correct. But again, here's evidence of these charged dust particles in the Saturn environment. And then there are just a whole variety of astrophysical systems in which in which dusty plasmas are of interest. Some of them are these so-called noctilucent clouds. What that means, this is a cloud that appears to shine at night. So what you're seeing here is this wispy structure here of a cloud-like formation. These are water ices that have coalesced very, very high up in the top of the atmosphere, somewhere around 80 to 100 kilometers, well above the terrestrial clouds that form most of the weather that we see. And they are illuminated by the sun when the sun is far below the horizon. That what gives them these kind of structures. Planetary rings and, planetary nebula and star-forming regions, kind of these the planetary nebula that you see here that I alluded to before. And then the tails of comets. This is a photograph that, in fact, my daughter took of the so-called comet Neowise that was in the skies last summer. And you can see this long tail here that's made up of these dust particles that are interacting with the local plasma around the comet. And so astrophysical phenomena have always been driving this question of what are dusty plasmas and how we study them. So in the laboratory, how do we make these systems? Well, first of all, we would have some sort of setup that makes a plasma, something like this. So this is a glowing plasma that we form. And then we take particles, and we need these little, in this case, these little glass beads. Typically, these glass beads are micron size, so they are just a little bit bigger than human hair. So what we do is we have a little shaker or something. We take those beads and then we put them inside the plasma. And while they're in the plasma, you can't really see them. So we have to do something to illuminate the particles. So we take a laser, and then we take the beam from that laser and expand it in a certain way, and then take a camera, and then look into a part of the experiment. And then what you get are something that looks like this, where here's the purple glow of the plasma, the green that you're seeing is the laser that's actually that's illuminating the system. And then this little structure here and these other little structures there that you're seeing in green, those are the dust particles that are actually suspended in this particular experiment. And these are micrometer size silica glass beads, microspheres, that are suspended in an argon plasma and forming these really fun little rotating structures. There is another way that you can actually make a dusty plasma in the laboratory, which is particularly relevant for both industrial processing as well as astrophysical systems, where you start off with just a basic plasma, and then you inject some other kind of gas that has some sort of chemical activity. In the particular pictures I'm showing here, these are by injecting acetylene gas, which is a hydrocarbon gas made up of a mixture of carbon and hydrogen atoms, into an argon plasma. And then over even just a few seconds, what you have is a laser that's shining into the experiment. And what you see, this little cloud of material that's getting brighter and brighter, these are the dust particles that are actually growing inside of the plasma. And so this is another way that we can actually make a dusty plasma in the laboratory, either to inject preformed particles or to actually grow particles and put them into the plasma. And so The whole idea of this field of dusty plasmas, it's extremely interdisciplinary. It covers, say, on the horizontal axis here, things like fundamental physics, space phenomena, and various applications. And then the processes that we're really interested in are things like how do those particles become charged? How do they float in the plasma? How do they grow in the plasma? And these are just some of the examples of the kinds of things, from fundamental physics questions that we're interested in, for example, atomic processes, or how the particles in the plasma interact with the dust grains, to really important applications like microelectronics fabrication or how spacecraft become charged. And so we believe that dusty plasmas are this very interdisciplinary field that links together fundamental physics questions, space phenomena, as well as a whole variety of societal benefits. And so with that, I'm hoping that convinces you that putting these little particles into plasmas or growing those little particles actually is a kind of a physics problem that is really broad, and one that touches on some really interesting questions having to do with space and astrophysical systems, down to things that are really practical, like how do you make microelectronics. So, but I'm a physicist, and so okay, here are all these this is this big picture about how this system behaves. How do we actually study the physics of these systems, and what are the kinds of questions that a physicist might ask that might make this system really interesting? So that takes us to the second part of this talk. When I say I want to study a dusty or a complex plasma, what are the kinds of questions that I'm asking? And not only myself, but and my students, how do we actually understand the physical properties of these systems? So let's go back and actually take a look at what we mean by a dusty plasma. And as you saw in the images in some of the movies before, what you have is this glowing system. This is this plasma. A plasma is an ionized gas, and it is made up of positive and negative particles. The positive parts in most laboratory plasmas, those are the ions. Those are atoms in which you have an electron or two that have been stripped off, so they are positively charged. You have a sea of electrons that's in the mix of there, and those electrons are small and negatively charged. Because of the nature of a lot of these systems, the systems are what are called partially ionized, which means that you haven't turned all of the neutral atoms into ions and electrons. So you still have a lot of neutral atoms available. And then you've got these relatively speaking, these very, very large dust particles in the system, which are going to be from nanometer to micrometer size. And so you get this soup of positive ions, negative electrons, quite large dust grains. This is not to scale. And then those dust grains will collect the ions and electrons. If you have an environment that has radiation in it, let's say like ultraviolet light, that may interact with the dust particles and also change the charge of them. And so what ends up happening is that the plasma and the dust are actually then end up being coupled and linked to each other through the charging processes that connect the plasma and the dust grain. In the laboratory, what this looks like, this is a blow up of now part of a dusty plasma experiment in one of our labs, is this very, very rich system. You can actually see on the right side of this image individual particles, some of them that are fixed, some that are rotating. And then you can also see collective behavior. For example, you see these waves here on the right side of the image. And this is what, from a physicist's point of view, makes these systems so exciting. Not only can you see the individual particles moving in the system, which we refer to as kinetic behavior, you also get to see things like waves propagating in the system, which we call collective behavior. So a dusty plasma bridges the gap between looking at both the collective behavior, the wave motion, and the kinetic behavior, the single particle behavior in the system. And as I indicated before, these systems occur in all sorts of scales, from light years when you're talking about planet forming systems, all the way down to meter scale or even sub-meter scale when you're talking about plasma processing or sort of the fundamental physical phenomena you see in these systems. Okay, so if you've ever seen a talk on by any plasma physicist, they almost inevitably will show this picture. What it is, it's a way of classifying where you find different kinds of plasmas. And the way we do that is to use two numbers. One is the density, basically the number of particles per, the number of charged particles per cubic meter on one axis, and then we put temperature on the other axis. And so down in this lower right corner here, this is where you get solids, liquids, and gases. And so as a plasma physicist, okay, that's cool. I'm not super interested in that stuff. I'm interested in all this other stuff up this part here, where you see aurora and flames and space plasmas. And this is where plasmas actually exist. And so where dusty plasmas are kind of in this lower quadrant, this lower left side of the system, where you've got still a pretty moderate temperature of these systems, as well as a fairly low number density. And that's typically where you find dusty plasmas in this space. So let's talk about some of the properties that make dusty plasmas from a physics point of view quite interesting. The first I've already kind of alluded to, which is the fact that the dusty plasma collects charge. And so if you imagine here's this dust grain, and there's, back to my cartoon here, of these electrons and ions that are now attached to this dust grain. Here's UV radiation, maybe changing some of the charge. So as I said before, the dust particles and the plasma are going to be coupled to each other, linked to each other through the amount of charge that's in the system. And what you get from a physics point of view, we can write down an equation that basically tells you how many electrons are coming onto the dust grain, how many ions, using other processes called secondary electron emissions, is what this SEE is. Thermionic emission, what happens if the grain is very hot. Radiation effects, using this H nu term. And all of these are going to be functions of the properties of the plasma, which means then that the dust grain charge is actually fluctuating and it's changing as the system evolves. If you are so interested, you could actually write down even more equations for this. And what we do is we typically would write down equations for each of those terms, the electron part, the ion part, the UV part, and then we would solve the equation where we're taking all of these different currents, we sum them up, make them equal to 0, and then what we do is we solve for a particular value, which is the surface potential of the grain, and from there we can make a prediction of what the charge of the grain is, and then carry out experiments to test that. The second fundamental property of a dusty plasma is the fact that the dust grain mass is large. So if I am considering the properties of a typical dusty plasma, the electrons are very, very light. Their mass is something like 10 to the minus 31 kilograms. I consider the ions in the plasma. Their mass is going to be something like 10 to the minus 26, 10 to the minus 27 kilograms. Bigger than, something like 2,000 to 10,000 times more massive than the electrons, but still quite small. The mass of a dust grain is something like 10 to the minus 14, 10 to the minus 15 kilograms, which again, compared to my mass, which is probably closer to about 100 kilograms, is still really tiny. But that mass of the dust grain, that 10 to the minus 14 kilograms, is still something like 10 or 12 or 13 orders of magnitude, 10 to the 13 times bigger than the mass of the ions, which, remember, is another 10,000 times bigger than the mass of the electrons. So therefore, this has important consequences for a dusty plasma. And one of the ways we can calculate that is through a calculation of something called the plasma the plasma frequency is a fundamental frequency of oscillations. And for the electrons, if we plug in all the numbers, we can say that the electron frequency that you get is going to be 90 megahertz, 90 million oscillations per second. For the ions, that's going to be 330 kilohertz, 330,000 oscillations per second. For the dust grains, however, that number is only something like 20 hertz, or that means 20 oscillations per second. Now, what does that all mean? It means then that there is a separation between the electron behavior, the ion behavior, and the dust behavior. And the dust is really, really slow compared to the electrons or ions. And from a physics point of view, the way we would describe that is to calculate something called the charge to mass ratio. And what it means is that the charge to mass ratio for the dust is really, really tiny compared to the ions. And that number is small compared to that of the electrons. And from a physics point of view, that's the fundamental physics. Large mass means small charge to mass ratio. And it changes then the dynamics of the system. Now, the third part, the third fundamental property of a dusty plasma is really at the heart of why of this talk and what makes dusty plasmas really interesting. So when one talks about the properties of a dusty plasma or any plasma, there's a term called represented by this symbol capital gamma, which is called the coupling parameter or the Coulomb coupling parameter. It is a measure of how well and self-organized a system is. And it's not specific to plasmas, it's a general term that we can write down for any kind of system. In the context of a plasma, it is the ratio of what we call the electrostatic potential energy. That's basically the energy stored in the electric fields between the particles, divided by the thermal energy, basically how fast the particles are moving around in the system. And I promise you that there are three movies running here. There's a movie at the top, a movie in the middle, and a movie at the bottom. Now, in the bottom movie, and these three movies are all of the same dusty plasma. So this was an experiment carried out by our colleagues in Germany, in which they made a dusty plasma. They with the same particles, and then what they did is they adjusted the conditions in the experiment so that for the early part of the experiment, this quantity gamma was much less than 1. And when gamma is less than 1, a system behaves like a gas. This is not unique to dusty plasmas. Any system in which you can write down the gamma and it's less than 1, it will act gas-like. And then you can change the conditions in the dusty plasma experiment to make gamma about roughly equal to 1. And in physical systems, when gamma is of order 1, you get the system behaving like a liquid. You can see the particles moving, but they're not moving very fast, and you can kind of see sort of slow motion through the system. And then when you change gamma again by adjusting the conditions in the experiment to make gamma much, much bigger than 1, the system actually crystallizes and becomes to act like a solid. And again, this is the same experiment with the same dust particles, and all we've done is change the conditions in the experiment so that you can make the dusty plasma behave gas-like, or liquid-like, or solid-like. And again, I promise you, all three movies are running. You can't really see very much motion in the top movie because that's the whole point. It's actually crystallized and solidified and begin to act like a solid. And that is one of the most remarkable features of a dusty plasma, is that in a plasma state, the system is a plasma. You can put these dust particles in it, and then you can use them to study gas-like properties, liquid-like properties, or solid-like properties, all inside of a plasma, which goes all the way back to the beginning of the title of the talk. A dusty plasma can be made to represent not just plasmas, it can represent all the different states of matter, solids, liquids, and gases, which I think is extremely interesting. And so going back to this plot that I had before with density on one axis and temperature on the other axis, there is a way of incorporating this gamma effect. You don't really have to pay too much attention to the details, but I do want to point out two things. Now what happens is that the dusty and complex plasmas, based on their parameters, will now sit in this broad area of space here in kind of this gray box. But what's really cool about it is that if you take solid state systems, so-called solid matter systems, things that are called colloids and things like that, then their parameters in this density temperature space look very similar to the properties of a dusty plasma. And it is that fact is why the dusty plasma can act solid-like, liquid-like, and gas-like from a fundamental physics point of view. So now what I want to do is I want to turn to two specific examples of a dusty plasma in the laboratory. One is going to be looking at how to use dusty plasmas to study solid-like behavior. And then the second one will be using dusty plasmas to study liquid-like behavior. And for this first one, the solid-like behavior, this is the work that's actually being carried out here at Auburn in our facility called the Magnetized Plasma Research Laboratory. This is a laboratory. It's funded by the Department of Energy as what's called a shared user facility, but the equipment itself was actually funded by a combination of National Science Foundation, Department of Energy, and NASA funds. And the central facility that I'm going to be talking about, which is the Magnetized Dusty Plasma Experiment, is a facility that was funded through the NSF MRI program. And that is this large facility right here. We have a number of experiments that we do. This is MDPX, which I'll talk about a little bit more in detail. We have a linear device called Alexis. We have atmospheric pressure plasma experiments that were done in collaboration with our colleagues at CPU2AL. And so it's a really quite a fun facility with lots and lots of things, lots of different experiments that we can do. So the focus for specifically talking about dusty plasmas in their solid-like mode is going to be done using this MDPX, or magnetized dusty plasma experiment. It is a large experiment. It is from the ground, which is just outside the field of view here, to the top of the device, is almost 13 feet tall. It has a large set of superconducting high magnetic field coils inside these black chambers here in the top and bottom. And then we put the experiment here in the middle in this gap between the upper magnets and the lower magnets. For those of you that have a background in plasma physics, you can see the various parameters that we have here. It's pretty much a fairly typical RF generated low temperature plasma, but operating with this is quite large magnetic field. For a low temperature plasma experiment, we also have the ability to control the gradients and other properties like that. So it's we're quite pleased by this because it's a fairly unique facility with an enormous amount of diagnostic access, because you can access the machine from both the top and bottom, as well as from the sides, and it gives you lots of ways to look at the experiment. So to looking at a dusty plasma as a solid-like system. This was work that was done by my students. It was a discovery that we made in the high magnetic field system. And the basic configuration is we made a dusty plasma like we normally do. And we have a camera looking down in the experiment through the top, and a laser lighting up the particles. And then we have another camera looking in from the side. And we began looking at the experiment, and one of my graduate students said, "Hey, Doc, the particles are moving in straight lines." Now, if you've ever, for those of us that work in plasma experiments, that's a very odd statement. Plasmas generally don't do that. And my first instinct was, well, that's weird. We don't normally see that kind of behavior. And we began looking at it. And if you take the movie that's playing here on the left and you add up the individual frames and add them all together, lo and behold, you do in fact see these particles moving on these straight lines, and even weirder, making 90-degree turns, jumping from one location to another. To us, that was really weird. And this phenomena seemed to be dependent on the gas pressure, because at high pressures, the particles basically would just rotate around like we expected. At medium pressures, they began kind of beginning to form these odd patterns. And then by low pressure, they really did form these really strange grid-like structures. And so it turns out, however, that it was actually coupled to part of how the experiment was designed. We have a wire mesh that is in the upper part of the experiment. And it turns out that the size of that wire mesh was actually being imposed onto the plasma, and the dust particles were somehow finding that pattern. Now, that might seem kind of obvious in retrospect. However, if you take the parameters and you take some of the considerations for this experiment, the fact that it was operated at reasonably high pressure, it means that the ions and the electrons were quite collisional. This was really hard to picture. How is it that a wire mesh that is in fact 30 or 40 or 50 collision distances away from from where the dust particles were, how did the dust particles know, quote unquote, that there was this wire mesh there? That was really quite fascinating. And it's been a subject of the research that we've been doing for several years. So one of my PhD students, Taylor Hall, actually this was the subject, a large part of his PhD research. And what he was able to do was not only just say, oh, here are the here's how the system behaves, and we can just see these different kinds of behaviors. He actually came up with a really cool way of being able to classify the different kinds of motion that we were seeing. And Taylor was one of our CPU 2AL supported graduate students, and this was kind of the centerpiece of his PhD. And what he identified was that there was kind of multiple or three main categories of particles. One set that we called uncorrelated, where essentially the particles did not know that the wire mesh was there. And this would occur at either low magnetic field or at high magnetic field, but also at high pressure. And so it gets to be a complicated kind of mix of exactly what's actually happening. There is what's called ordered flow, where the particles seem to be circulating, but they're moving around on the mesh. And then with this other region we call trapped, where the particles were actually became fixed in space. And what Taylor was able to do was to actually take these three different regions and actually map them over a wide range of experiments, and to show that we could actually classify these different particles based upon how well magnetized the ions were. And it's really quite a wonderful set of experiments. But now that we've classified these things in the experiment, we've shown that we can now take this highly magnetized dusty plasma system and make it act like a solid. It's still the question of, how did that actually work? Well, this was then became the work of a second PhD student who was also a CPU 2AL supported student, Mohammed Manati, and he worked not on the experimental side, but actually on the computational side. And he, in fact, built a fairly advanced three-dimensional two fluid model system that is shown in this little cartoon. Here are the kind of wire meshes that he built into the experiment, into the simulation. He added a magnetic field. The system, while not exactly representing the experiment, had dimensions that were comparable. And in fact, actually, what he was able to show is that it's a little hard to reconstruct out of this, but in fact, he was able to show that indeed, where you got the confining of the particles was along the wires, depending upon the dimensions of the system. But more importantly, from his simulations, and this is the one that's kind of the punchline, is that he was able to show that you can form structures that extended fairly deep into the plasma from the wires, several centimeters into the experiment. And when you actually calculate the electric field, which is the electric force that you need, which is the source of the electric force that you need to suspend the particles, he was able to predict where the particles would actually become levitated in the experiment that was consistent with what we saw in the experiments. So using a combination of experiments, the work done by Taylor, and simulations using the work done by Mohammed, I think we've actually begun to build a picture of what's happening, in that we're getting trapping structures that are formed due to a competition between electrons and ions in the system. And that competition gives rise to vertical structures that are in the plasma that the dust particles then find, and then form these square-like, grid-like patterns that represent, that reflect the behavior of the larger system. And so this is really kind of a fascinating tour de force, representing something like 4 or 5 years of work, several PhD students, to be able to understand the solid-like behavior of a dusty plasma. So the final topic then is going to be, how do you use dusty plasmas to study liquid-like behavior? And this is an equally fascinating project done by our group and my PhD students. So what makes this particular project really fun is that early on in the work of the dusty plasma community, going all the way back to the beginning, I remind you that the mass of the dust particles is very large compared to the ions and electrons. And the charge to mass ratio is very small. And so one way to overcome the large mass of the dust particles, it turns out, is to find a way to make the mass irrelevant. And one way to do that is to take your entire experiment and put it someplace where mass isn't going to be that important, or more importantly, the effect of gravity on your system is not going to be that important, which means taking the whole experiment and putting it in space. And for almost roughly 20 plus years, the dusty plasma community has actually been running experiments in microgravity, first starting in the late 90s and early 2000s with sounding rockets, conducting experiments on the Mir space station. And then since the early part of the 2000s up through today, have been carrying out a series of experiments on the International Space Station. The most recent of those experiments is called PK4, for plasma crystal 4. And that's where we're actually going to talk about these liquid-like dusty plasmas. And so this experiment is based on the ISS, on the International Space Station. There's a module, I believe it's right here inside the European Space Agency module. PK4 is a joint Russian-German experiment that is hosted by the European Space Agency. What we do in our laboratory is, one of the things that we do is we have techniques that can measure the velocities of the particles. This is some data from the calibration of PK4 in space, which are the commissioning of PK4. What you're seeing on the left is an image of the particles that are being pushed by a laser in microgravity. And on the right, what you're seeing is using our analysis techniques to actually reconstruct the velocity and the motion of those particles using a technique called a particle image velocimetry, where we use a laser to light up the particles and a camera to record it. And then we have analysis techniques to measure the velocities. And so one of the things that we want to be able, what we can do once we have all of those velocities, is to measure something called the velocity distribution, basically binning up all of the velocities in different regimes. And when those particles are flowing, if we can actually make a map of what those that binning looks like, we can then fit the data, which is the red points, with a model, which is the blue curve. And from that blue curve, we can actually extract out information about the thermodynamic properties of the system, the temperature and the flow velocities and things like that. So in PK4, what you get are flowing dusty plasmas because of the way the experiment is set up. So basically what you have are two electrodes, and you have this long tube sitting here in the middle of the experiment, and you inject particles using these little injectors that are shown here. The particles then go into the experiment, and then they flow along the length of the experiment. And then by programming the currents on the electrodes, you can have a program where, for example, you have a current that's, say, positive, where the particles are going to flow in one direction. Then you change the current, the direction of the current in the system, you get a flow reversal, and then the particles begin flowing in the opposite direction. And then you can also then program the current to oscillate back and forth to do trapping of the particles, which is a phenomenon known as polarity switching. And what it does is it modifies the coupling between the ions in the plasma and the dust particles. And then what we can do is we can program certain kinds of behaviors by adjusting how the particles are flowing and how they are, and what happens during polarity switching. So an example of that is shown here. Here are the particles flowing inside of the system. Let me start that over again. And you can see up on top, here's a movie of the particles moving back and forth. And then here's just a loop of what that corresponding velocity fields look like. So you can see the particles coming in, they're flowing to the right, and then at some moment they flow back to the left. And this is showing it before you actually engage in the trapping. So this is a dusty plasma that is on board the ISS that is executing fluid-like behavior. And this is the heart of the work that's done by another CPU 2AL student, Laurie Scott, one of my PhD students whose work I'm going to highlight next. So one of the really cool things when you actually take a look at this data from the space station of these flowing dusty plasmas, we did a series of experiments on the ground to try and understand, as you stop the particles, what actually was happening. And specifically, what is happening to the flow of the particles, their velocities, and then what was happening to the temperature of the particles, essentially the energy of the particles at this moment that you stopped. Well, what first of all that happened is that the upper part of these two plots on the top represent velocity. The bottom two plots represent temperature. If you want to think of it, this is sort of the velocity of the system, and then this is the energy contained in the dust particles. You get, first of all, when you stop the particles, when you turn on polarity switching, you get this rapid decay of the motion of the particles. And this was good. This is what we predicted. If you have a flowing set of particles and you have a certain amount of gas in the system, there is a known phenomena called the Epstein drag. And this would tell you that within 1 to 2 video frames, depending on how fast your cameras are working, but for this experiment, within 3 video frames, all the particle velocity should slow down, come to rest. And what you're seeing here is the particles drifting at something like 14, 15 millimeters, or maybe 15 millimeters per second. And within a couple of frames, their velocity comes to rest. This is the direction here along the electric field in the plasma that's pushing the particles, and this is in the perpendicular direction. Now, what was truly surprising is that even though we stopped the particles, the particle motion has come to rest. What happened is you saw this moment, this heating of the particles, energy was being transferred into the particles temperature went up. And then much, much longer than this 3 video frames, what you see is this long extended decay that almost lasted 40 video frames in the direction along the electric field, and then here in the direction perpendicular, not quite as long, not 40 frames, more like about a few frames after polarity switching, and then decaying for about 7 or 8 frames, maybe 10. Here is this heating that's occurring in the system, and really changing the dynamics of the system. First of all, this does not happen on ground. When you do the same experiment on the ground, you see the energy decay and the velocity decay basically occur at the same time, over the same time period. microgravity changed the behavior of the system. So first of all, that was incredibly exciting to Lori. It means that our experiment worked, that we did something in space and it really made a difference. But then we have to explain what exactly is happening here. And so a lot of Lori's work has actually been focused on trying to understand what happens in that first few moments right after you do this polarity switching. So this is kind of zooming in here on the first few time frames after the polarity switching occurs. So this is these data points here, the first 4 or 5. The first few data points are the black dots that you're seeing in this figure on the right. So this is the experimental measurement. And then what you're seeing here is a series of simulations that Lori has actually run and developed for trying to understand some of the mechanisms that are occurring inside the system. And you can see there's too many details that I don't want to go into at the moment, but suffice it to say, we're actually have made sufficient progress where we're now getting close to being able to predict, or at least model in a pretty reasonable way, what's actually happening inside the first few video frames right after this polarity switching effect. And it looks like we are able to both model the slowdown of the particles and also the extended heating of the particles. And so this is something that's really exciting to us because we think we're actually being able to get a handle on what the underlying physics is. And so this is our ability with these two experiments to kind of describe what's happening with a dusty plasma that's behaving in a solid-like way in a high magnetic field experiment and in a liquid-like way in a microgravity experiment. Okay, and so to get to the end of this and to summarize, dusty plasmas are just cool. They are this remarkable, amazing system. You have phenomena that we're looking at that are very fluid-like, as in the microgravity experiment. They're very solid-like, as you see in this high magnetic field experiment. And then in an experiment I didn't talk about, this is a hybrid experiment. This is one in which you see some of this self-organization in one part of the experiment, and then you also see this fluid-like behavior in the other part of a laboratory experiment. And so these dusty plasmas are really, really rich systems that you can use for studying not just the plasma, but also studying other states of matter. And to end our lab, these are just two of the examples of work that's being done in our laboratory. We have a wide variety of modeling efforts. We have the work by Lori, another former PhD student, Spencer LeBlanc, looking at solid-like and other kinds of self-organized systems in magnetic fields. We're actually also looking in work done by another PhD student, Stephen Williams, looking at exactly how the dust particles become self-organized. And not the dust, but the plasma itself. So these patterns that you're actually seeing in this figure here, there is no dust in the experiment. This is the plasma forming new kinds of patterns, and they've actually been simulated by Mohammed. We also look at charging and how we can control the charge in the system, and we've done a number of experiments with collaborators within and outside of CPU2AL on how nanoparticles get grown in the plasma, including some work by a former postdoc of mine, Serbi Jaiswal, looking at exactly what happened to these nanoparticles in strong magnetic fields. And so this is a really, really rich system that can study a whole variety of phenomena beyond just looking at the solid-like or liquid-like or gas-like properties. And so in conclusion, obviously this work is not done by any one individual. I've highlighted some of the folks that have worked on it. It's a really large team that works on a variety, that works on this with myself and my co-PIs. The folks in blue are some of the former graduate students, in green are some of the postdocs, and in red are some of the current grad and undergrad students that have worked on this project. And with that, thank you all very much. I hope that you were able to enjoy this presentation.
Thank you so much, Ed. I know everyone's giving you a virtual round of applause for your presentation. We don't have any questions at this moment, but if we get any, I'll definitely send them to you and give you an opportunity to address them in some kind of way. But thanks again, and thanks everyone for joining our talk today. Until next time, bye-bye.
Bye.